Okay, so after the long break, let's resume our discussions on approximation and generalization theory, right? So when we stopped 2 weeks ago, what we discussed was these various sources of errors when you fit your neural network or any classifier to your training data, right? So we know machine learning is more than just an optimization problem. It also needs to generalize well on the test set, right? And then the other issue is what kind of classifier do you take? Do you select a neural network or a random forest? What's the size of the neural network you select? Should you do 10 layers or 2 layers, right? So, which one is a better one? Right, and that's where we said one way to analyze those different sources of errors is to decompose them into various parts and then reason how these different classifiers, different learning algorithms would perform on these various errors. Right, so that it's better to kind of decompose the errors into multiple components and reason about each one separately. So that gives us more intuition.
Describe the estimation error again. Is that like having incorrect labels for your data?
No, so the estimation error is the excess risk, right? So that's the, what is the error of this optimal classifier? So if you optimized your population risk, you would get this H star. And then this would be the empirical risk minimizer, right? So on your training data, you're looking for the best classifier that minimizes the empirical risk. What's the difference between the two? So that's the estimation error, right? So that's one source of error. So the first source of error was approximation. So we said, if your function class is limited, right? So you're forced to choose in a certain function class. Let's say a 2-layer network with whatever, 20 neurons, right? So you fix the size of the network, then there are certain limitations, right? So you may not be able to perfectly approximate your function within that class, and that's the approximation error, and the other is the estimation error. Right, so the total error will be like the sum of the two, right? Because you have the component of, even if you had infinite data, so that's why it's called approximation, because this has nothing to do with the samples, right? So even if I gave you infinite samples from this distribution, right, drawn IID from the distribution, I wouldn't be able to do better than this. There would be a source of error. That's the approximation error. Then the estimation is with my finite samples, I will make an error because I'm only going to fit to my training data, right? So, and one of the standard things to do would be to minimize the empirical risk, right? So I have a certain loss function, I will minimize that on my training data, and the question is, how does that differ from the population level classifier, right, the best classifier. Okay, so that was the 2 errors we studied. The third one, which we didn't characterize, and in fact it's quite hard to characterize, is the optimization error, right? So a certain optimization algorithm, how well does it do? If it doesn't go to the globally optimal point, right, that's the ERM point, but goes somewhere else, how much worse is that? Right, so what is the difference between the local optimum and the global optimum? That depends on the optimization landscape, right? So that's typically hard to characterize, but we'll see today in the modern networks, this is typically 0. Right, so yes, it's, in the general case of non-convex problems, this is hard. In fact, these are NP-hard problems, so you could have really bad errors between the ERM and the point obtained by a particular algorithm. But in modern networks, we are seeing that this is typically 0. So that's kind of like what we will see today. Many of the errors in theory could be really bad, but in practice, they seem to be counterintuitively good in many ways, right? And there are some other unexplained phenomenon that's causing errors. So there is a lot of like gap between theory and practice. So that's what I'll try to reason about and ask, is the classical theory really valid, or do we need a new theory? Do we need new experiments? What are the missing pieces? And there are some very recent works that try to shed some light. I think they give us some very useful lessons. So I think to me it's very exciting that there is almost like a resurgence of new theory. That does draw on the classical theory we learned, but has many new ingredients. So I think there's a lot of potential for new research to be done in these areas. So that's what we'll cover today. We'll ask in modern networks what really matters, right? What can I reason about my approximation error? Is this really that bad? What about the estimation error? And ultimately, how does it generalize on my test set? How do I measure that, right? And as we said, the optimization error, many times I can overcome that. So what's the reason behind all this, right? Can we at least draw some intuitions? Can we come up with certain assumptions under which we can explain what we are seeing in experiments? So is this picture clear? So if you recall from last week, right, so what we said in the classical regime was this bias variance trade-off that takes place. So really this, this bias, we said one source is the approximation error, right? Whereas the variance comes from estimation. And so we want to trade off the two, right? Because, there could be some models, some class of models where the approximation error is large, but the estimation error could be smaller, right? In other cases, it's the reverse. So which one is a good class of models? Right, so this is like selecting the function class itself or the hyperparameters. So if I told you, you can have all the neural networks up to 10 layers, which is the best one, as an example, right? So somehow you have a certain class of models. Within that, you want to ask, how do I select the best model complexity? Right, so how do I choose that to balance both my approximation error and the estimation error? And what the classical theory tells us is it's a middle ground. You don't want a model that's too simple. So if it has too few parameters, we call that underfitting, right? So in that case, the approximation error is very large, right? So think of a linear model, right? So in the linear model, if you are trying to fit a highly nonlinear function, you will have a very bad approximation error. On the other hand, the estimation error could be quite small because, the variance when it comes to a linear model is more limited. And you can see that from the complexity of the function class, right? Like when we looked at VC dimension, Rademacher, all those gave us a bound on the estimation error or the excess risk. So that was the trade-off that, in this regime of too simple a model, you will have underfitting and you will have a high approximation error or a high bias. But in this other extreme of a very complex model, you can have a small approximation error, but your variance increases, right? So you shouldn't be doing both. You should look at the middle ground, right? So what is kind of the visualization? So if I had all my, let's say, data points in some space, right? So let's say these are my training data. Right, so if I try to do a linear model, I would do this line, but I would then miss all the points that won't be part of this line, right? So those are, if there are many points that are really not part of that line, then you can, it's not that regular, although that's what my figure looks like, right? So you can only draw one line. That's a linear model. You cannot do anything better than that. So you cannot fit all the data points, right? So in fact, your training error will be large because you cannot, even on the training data, you cannot fit to all the data points, but then your variance could be small, right? And we know that from the VC bounds that it will be small. But on the other hand, if you had a very complex model, you could try to interpolate through all the points. And so it's highly nonlinear, and the approximation error is small in that case. In fact, it's 0 if you interpolate through all of them, right? But your estimation error is large, right? And if you recall, that's again coming from these VC bounds, right? So if you recall, we said if it's, for instance, a linear classifier, it depends on the dimension, the number of, and even within the linear classifier, it depends on the input dimension. But also if you bound the norm, it's smaller. And if you had these multiple layer networks, if you recall, it was like the product of the norms of the different layers, right? The weights of the layers. So we had ways to bound the excess risk through these complexity measures, right? The VC dimension, the Rademacher. And basically what they said was this complexity measure increases as the number of parameters in your model increases, right? Unless you put other constraints such as norm constraints, right? If it was just any model within that class without that constraint, you would just be like a parameter counting, right? It would be like kind of essentially the number of free parameters that's coming up roughly in these complexity measures. And so that's kind of the intuition why as you increase the complexity of your function class, right, your variance is increasing. So that's given by all this generalization theory, right? So we looked at Rademacher complexity, the VC dimension, and so on. And so is this picture clear to everybody? I mean, this was the conclusion from the previous classes, but I want to make sure everybody understands this because, I mean, this is a solid theory, right? So there is nothing wrong with this theory, but we will, ask about its relevance with these modern deep learning experiments. Right? So what this theory is saying is you should not be choosing a very complex model. Right, so for instance, it's saying that don't choose a ResNet 100 or a DenseNet, right, with these nearly billion parameters. I mean, should you be choosing that? I mean, this theory does not explain that, right? Because the bounds start getting vacuous when you have over-parameterized regime, right? So even it's easy to see in the linear model. If you have a linear model with dimension d and number of samples n, and if you have more dimensions than the number of samples, that's called over-parameterized regime. So meaning you have more parameters in your model than the number of samples. Right, so that's the phenomenon of overfitting, right? Because if you have more parameters in your model than the number of samples, you can certainly interpolate all the points, right? So you can have like 0 training loss because you can perfectly fit to all the data points. And our entire classical theory is based on saying, no, don't do that, right? Don't go here. Don't go to this over-parameterized regime, or not even near the over-parameterized regime, right? So you should stop way before the overfitting setting where you're getting 0 training loss, right? So the philosophy is don't make training loss 0, right? You should make it not too small, right? And that was kind of the almost the conflict with optimization. If you recall in the first lectures, we briefly discussed that, right? We said, optimization tells us to go to the best possible error, and if there's enough capacity, that would be 0 error. But our classical theory is saying don't do that, because if you do that, you're overfitting and you can get a bad test error. right? So, and that's where the people have come up with all kinds of techniques to overcome that, right? So, one is these algorithmic regularization. So, one approach is you just stop early. So, you don't train until the very end. If you stop early, it's like a form of regularization. You're not getting a zero training loss, and in the classical regime, that's a better thing to do, because then you're likely to end up here in this region rather than the region up here, right? Or you regularize explicitly, right? And that's what we, for instance, see in these norm-based bounds, because if now instead of the ambient dimension you have the norm, right? Whether it's the norm of this weight matrix, for instance, then you can have a better bound. Right? So you may have a large number of ambient parameters, but not all of that affects your bound directly. So you can get a sharper bound than just the parameter counting. And so that's kind of like where we will see things are headed, right? Because these modern networks do have a lot of parameters, right? They can indeed fit training data perfectly. But what's not incorporated in these classical bounds is the effect of algorithmic regularization. So what this bound is saying is, in the worst case, right? So in the worst case, you would have this, excess risk bound. But there could be a better than that. It's only an upper bound. It's not saying this is how you will always do this bad. And if we are doing certain algorithmic tricks, like maybe the way stochastic gradient descent works, for instance, right? You could do better than this. But even accounting for all this, it seems like bigger seems to be better when it comes to modeling. And it's interesting to see what happens if you look at other aspects like shifts in distribution or in terms of adversarial examples, right? So these are all things we'll cover in the coming lectures. Thank you.